Okay, so let's continue with PageRank and what we were doing last time. We're going to sort of look at. I talked about the reason, the main motivation for PageRank was the fact that the traditional approaches that were used until that point for searching and showing you the results were very easy to sort of manipulate. And what has happened following PageRank and following Google is that the spammers are basically coming up with techniques, and it's basically a never-ending race of the spammers trying to outsmart whatever ranking algorithms you have and techniques to overcome that as well. So we'll take a look at some of those cases. Specifically, we look at topic-specific PageRank. So you might have seen this. Google does this very effectively nowadays, which is that if you're logged on and Google knows who you are, and you make a search versus some other person makes a search, the results are going to be different in the sense that they are trying to figure out what is it that you like. You know, how interested are you in sports? How interested are you in games or any topic? And based on that, try to do it, because most of the search queries, the typical search query that we enter in are generic enough. You might have a keyword. So depending on your own interests or what you're thinking about, the results might be different, which means that the PageRank itself has to reflect that. And this can depend on what your immediate history has been. Maybe you're looking to buy a car, and then you're making a whole bunch of search terms regarding cars, which means that by the time you're making third or fourth search, maybe the system has to be smart enough to figure out that now you're in, at least right now you're interested in looking for car-related terms, and so you want to push those topics a little bit higher, so increase their weightage. So how do you actually do something like this? And the related issues of spam. So we briefly talked about spider webs, and how you can artificially try to increase your PageRank. We look at it a little bit more mathematically, why it's a problem and how you might go about detecting that and correcting for those kind of cases. Assignment 2 will go up tonight, but there is a little bit of a delay because the machine is not available. Hopefully it'll be available tomorrow, and so Wednesday can be the official start date. Basically, you're going to implement matrix multiplication and PageRank, including some of the topics that we're going to cover today. Okay, so that's sort of the general thing. It's going to be done on Hadoop, and like I said, once the machine is up and running, you'll all have accounts, and I'll go through some of the aspects of running it on this particular system. Again, one other issue that I don't have it on the slide, but you should consider is you need to think in terms of, we sort of covered it, so that's why I skipped it here, is that V, right, the probabilities that the PageRank itself that you're computing, whether that's something which is stored on every given process, is it small enough that everybody can have that much memory, right? So you at least need 2 copies of that, right? One that is the incoming one, and one the output of the matrix vector product. You can potentially do it in place, but it's going to be messy. But at least that. And if we are not going to have it, then what is the appropriate strategy for dividing it up into chunks? And now when you think of dividing V into, let's say, a bunch of different groups, so that we can use the same strategy as what we discussed earlier for the matrix vector product or the matrix multiplication, you have to then think about how this gets partitioned across, the matrix itself gets partitioned to map one to. One extra consideration that you should have in this case is that we are going to be doing this iteratively. So we sort of ignored this aspect earlier, but you want that the V in and the V out sort of get mapped the same way. It has to be symmetric because you're going to be repeating this calculation again and again and again. So if I had VI spread across my processes a certain way, whatever style you choose, then at the end of the matrix vector product, the output should be divided the same way so that you can repeat it. Because you don't want to be exchanging this at that point to a different mapping. So this is something that you should think about. I'll have a link to a book chapter where they do go into this in further detail. So as you go about implementing it, you should probably read that section to think of the consideration. Keep in mind there is no one fixed way of doing it. There are general good ideas, and we cover some of these. But you should have this at the back of your mind, in this case, more than others because you're doing it iteratively. Okay, is that clear?
Actually, I still have, I'm just still hung up on this probability part.
Yes.
I'm assuming this is a simplified case because like you're assigning equal probability to
Yes.
all of the links.
Correct.
Assuming you have one page that has one link to each of the other pages, but 20 different links to the same exact page, that means you should have higher probability for that specific.
Not necessarily. So this is going to come, so we are getting into somewhat of heuristics at this stage. If a page links to the same page 5 times, we will give it extra weightage. And this is going to be a little bit tricky, guys. We are making an assumption here that you're somehow consolidating all the links independent of how many times it repeats itself, and there is an equal probability of going visiting any one of them. Rather than saying that if he links to the same page 100 times and there are a few other things, there's a higher probability, which is probably true. But we are, in this case, from a page rank perspective, we are ignoring it, right? But if you had a problem, and because now you're getting to the specifics of how exactly you want to define page rank, right? And keep in mind that what you're defining as a page rank, and we'll look at some variations now, it's not like an absolute truth. You are sort of designing it, or you're coming up with heuristics to avoid cases such as what the spammers might do, right? So there might be situations where we look at a specific case of how you would artificially increase the page rank of your own web page if you had to. And many of you might have noticed some of these things on the web, not realizing why people are stupid enough to do this, but you might realize now why some of these things take place. Okay? Bear with me a minute, we'll go through these cases, but the simple answer is that it's a specific case of how you want to define these. And that is going to boil down to the transition matrix as you are defining. And if you are defining a more complex transition matrix where the probabilities are going to be different, maybe depending on what kind of links are around the top, the text around the link, in which case you have no option but to go for the general sparse matrix format, because then the probabilities are different, right? Here we're just using our knowledge of the structure of the matrix to further compress it, that's all. And you'll always have this choice. Maybe if you have some in-between model for your transition matrix, then you can use not these schemes, but something else which will give you the compression. So I talked about it, I briefly mentioned this in the beginning of topic-sensitive page rank, which is that maybe you're searching for cars and you want page rank to reflect that. More generally, all of us have different tastes. So maybe I'm 25% interested in sports, 50% interested in politics, and another 25% interested in cars, right? Whereas this is going to be different for any of you. So the general idea is to weight certain pages more because of their topic. And these topics should reflect either my own personalization, so that it is personalization of the results to a specific user or to a specific query. The general mathematical idea is going to be the same, whether you personalize it to the query or to a user. The simple way of doing this would be that there is a special page rank for every one of us, which is a reflection of how likely I, as a random surfer, am to be on any of these billion web pages that exist, right? So as you go in and you do your searches, or somehow you have conveyed to this, you have, let's say, trained your own way of this. And if you remember, many of these online shopping websites, or let's say Netflix, for example, early on, gets you to rate how likely, how much you like a particular movie, for example. Those are effectively creating a personalized profile for you. And that's what it is. But of course, this is not scalable when you consider web pages, right? You have billions of pages, and I want to store a floating point value, which is the probability for each and every of these pages. That's too much storage for a given user. It doesn't make sense. It doesn't scale beyond. Maybe, the top shots at Google have their own, personalized page ranks, but not for everybody else. And it in general doesn't make sense. The alternate approach, and you will see this used across data analysis and scientific computing, you'll see it across a lot of fields, is to really create a set of basis vectors, right? So you're saying that I'm going to create one vector for a small set of topics. We can call those as basis vectors. You can either decide what these topics or these basis vectors are independently, like manually defined. So, the head search guy at Google says that I think these 15 topics are enough to characterize everybody. Or you can actually go ahead and analyze a lot of these web searches and interests of people, or try to classify all the web pages depending on what topics are enough to cover the entire spectrum. And later on in the class, we'll look at how you have given a set of data sets, whether it is web pages or anything else, how do you actually try to figure out these representative samples, which you can call here as basis vector. Now let's for now assume that these are hard-coded. Let's say it's news, politics, whatever, sports, finance, a set of topics that individually try to characterize these. We will determine the page ranks which are weighted for each of these topics, which means that if you're on ESPN.com and some web page and you're looking at the sports-specific website, then that's going to get a higher rating, a higher page rank. Whereas, let's say you search for cricket and it's focused on the sports part of it, then all the ESPN or any other web pages talking about cricket, the sport, are going to go up. Whereas if you're more interested in, say, nature, then the insect cricket is going to get a higher rating. Or maybe if you're looking at science and technology, the mobile service provider cricket is going to get a higher rating. So this is now for the same search, depending on your interest, you can focus it on this. Whereas, so if he searches for cricket, it doesn't show him cricket related to the sport because he's not interested in that.
So the bias I'm putting it on is after I create the transition matrix or before I calculate?
We'll get to how exactly we're going to do this. But basically, we are going to create a separate page rank, which is going to incorporate, which is going to be biased towards one of these guys, your topics. So if we say that there are 100 such topics or 100 such bases, then we're going to have 100 page ranks. Now what I can do is that for each individual user, right, either dynamically or in a fixed fashion, I'm going to figure out where your interests lie with regards to these chosen set of topics. Yes?
So who does this personalized build? Who does this work?
Who does as in?
Yeah, like who uses this algorithm?
So
because what companies use, like including Google,
I think Bing uses
it's
it.
good, huh?
Bing uses it.
It doesn't use. I mean, for Bing, I'm not sure, but for let's say for many big engines, what they do is like they have one page rank, they compute the vector of weight, they do just preview based on your personalized history. That's what they do.
A random permutation is not going to help because it's
I
going
didn't say random permutation.
Yes, so basically
Permutation is based on your personalized history.
No. So the way you would combine these together, right, is going to be different, and there are different strategies for it. What specifically they use is going to be different. Actually, I can tell you that from friends of mine who work in these cases, is that it's possible that when you search, you're actually getting a different algorithm which is deciding this. So most of them still continue to experiment on most of you as users. So there are different strategies for taking, say, the common page rank versus each of these specialized topic-specific page ranks. And you can think of different strategies for combining these together to give you the results. And there are different ways of doing this.
Yeah, but none of them are having a separate page rank for the user.
Nobody has, I didn't say, so you're missing what I'm saying. Nobody has a separate page rank. What you have is you have a page rank for a set of topics, which is basically trying to characterize your interest into these, and then when you search for it, you're combining these particular, because having a specialized page rank for yourself is not going to scale. So what they do is to have it on a set of topics, and over time, as you keep searching on Google, they can figure out that you are a computer scientist. So if you're searching for languages, there is a higher chance that you're interested in programming languages versus, say, spoken languages, and so on. So you are then building a profile for yourself, which is only a function, and it's the size of the basis vectors. The size of the basis and how they are determined is going to be different across different companies and different strategies that they might use. But it's not a one-step thing. So what you're doing is that for each user, the amount of data that I would store for this personalization is going to be the size of the basis vector and not the size of the full problem. So in this case, a simplified example is where we choose a set of topics. But in general, this could be arbitrary. So you're doing it in a sort of a two-stage process.
Is it like the same algorithm, same code running, but with different parameters for different people, and those parameters are learned over time?
No, so what you would do is that, so you're breaking up this problem. If you have, and we'll sort of look at some other examples. It's a very common scenario, right? If I had to build a different page rank for everybody, that's too expensive. At the same time, if I had to even build a subset by having to train or recompute the page rank for every single user, that is also intractable. Not from a storage perspective, but from a computation perspective. So you really break it up in both compute and memory into two stages. In the first step, I'm like, independent of how many people there are, I think I need only 10 page ranks variations.
So you mean people are segmented based on their behavior?
People are not segmented. You first segment the web pages or the page ranks into same arbitrary tastes. And this might be, like I said, if you do it in a manual fashion, it might be breaking it up into things like sports and entertainment or movies or whatever, which makes sense from a human perspective. But more realistically, you should really look at the scope of the distribution, right? And then figure out the right basis vectors or right representation, let's say right topics that you should compute this for. So you've first taken all your web pages, and instead of computing one page rank, you compute a set of page ranks which are all biased towards different topics. Ideally, in a mathematical sense, you want these interests to be orthogonal to each other, right? So that you're maximizing the separation. Once we have these different classifications, these biased page ranks, when it comes a matter of me deciding, all I need to know is, based on these different topics, where do your interests lie? You are mostly interested in science and only somewhat interested in entertainment, or maybe it's the other way around. So then, when it comes a choice, when you do a search, I can compute which pages are on the top depending on each of those different topics. And looking at your interest, you're more interested in sports. So I will sample the sports biased results more heavily than the entertainment one. So that's what you do. So the personalization for you is only limited to these topics. It's a much smaller problem. Yes?
Isn't your personalization vector still pretty big because there's so many different topics? Is that
so this is up to the user, right? So it depends on how many topics you need. Keep in mind that that's the dimensionality. So that even if you choose something like, let's say, 10 subjects, right? And try now not to think in terms of explicit subjects, right? As in sports or entertainment. The number of possibilities, even if I say that I'm expressing the level of your interest in one of these topics with just a byte, I'm giving 255 different intensities. The number of possibilities is 255 to the power 10 in terms of the number of profiles that I can store. So that's actually a very, very large space. So you are storing only 10 bytes per user, but the scope of variations is very, very large. You understand? So we don't. In reality, it's probably somewhere, like 10 to 100 topics. I doubt if it's going to be more than that. And when we can actually later on figure out how to estimate how many topics you will need. You can actually analyze the structure of all these web pages and figure out how many actually you need. And it's sort of related to how we did the page rank in the first place. In the page rank, we were computing the first eigenvector. We can actually go ahead and look at all our web pages and compute all their eigenvectors and their eigenvalues, which is going to tell us how much information that we need to store. And this is not going to be on the web pages themselves, but the topic of the web pages. Okay. Again, remember we are determining weights for each individual users, or in a sense, dynamically doing this for the set of queries that you might have. And this is going to depend on what sort of a search engine you're deciding. The size now we store, I just mentioned this, but I'll repeat it. The storage per user is just going to be the number of basis vectors and whatever variation that you want to store for each of those. Is that clear? Let's look at it again, it'll come back. So fundamentally, we're going to use the same idea again and again. So this is basically called a biased random walk. We were doing a random walk earlier, which meant that at any given instant, we had a finite probability of clicking on one of the links on the page, or 1 minus that probability of randomly appearing on any of the web pages across the world, right? The biased version is only going to appear on pages that are identified to be specific to that topic. So you can think in terms that if you're a sports fan, you want to increase the probability that you will be on a sports web page, which means that when I'm generating my random reappearance, that's going to start off from a sports page, which has been identified. And we can talk about how that's been identified. What does it do? It increases the probability that I'm on a sports page or pages that are reachable from these sports pages, say from ESPN or any other sports website out there, right? And the probability of me being on a random page decreases as the distance from one of these identified topic pages, the further removed you are from these, right? Is it clear? That's the intuitive and the mathematical counterpart for it. So when you reintroduce your random surfers, you're only reintroducing them there. And so what you do is that you identify a set of pages. This is not all your web pages, but pages which correspond to your topic. And this doesn't have to be the entire set, it's just a representative set, right? And now, earlier, if you remember, this was 1 minus beta, 1 over n, where n were all the web pages in the world. Now it's limited only to the ones which are specific to the topic. Is it clear?
No, but like, though my interests are into something, and if I'm checking something else, but then if those pages are...
This is not you as a person. This is a random person, but this is a random walk which is biased towards a particular topic. So now you have to think more one-dimensional. You might not be one-dimensional, but this particular surfer is very one-dimensional. So it's going to be specific to that topic. This is not you specifically, right? Eventually I'll use a bunch of different biased page ranks and combine it together for a true human user, right? So in this case, so think both from an intuitive perspective as well as what it means. Mathematically, actually, it's very, very simple because we're making only a small change to our formulation that we had earlier. But the core idea you want to see is that these set that we have identified, and these can be identified either manually, which means that Google can decide that these, you have web directories. Earlier on, Yahoo used to have a very, I think it's being closed now, but Yahoo used to have these directories of web pages. And based on those topics, or based on those classifications, we can figure out which of these web pages correspond to these specific topics, and then use those to reseed our random surfers, right? Is it clear? So fundamentally, you're identifying a subset of the internet and saying that these represent this particular topic. And all pages which are related to this, or their page ranks which are related to this topic, should be close to these representative pages. That's all. Make sense? Or right? So that's what you would do for this case. And once we have done this, this is how you would basically use it in practice, that you decide which topics we're going to create specialized page rank vectors for, and this could be done manually or from data. This particular thing is a challenging thing. We'll look at how you can actually create these kind of topics from a bunch of data. For each of these, we're going to create a set, and this set, if manually created, would also have to be manually identified. If we do it from data, we can actually use those as a representative for each of these as well, if we are sort of clustering all our web pages into these different cases, right? Later in this talk, if I have time, I'm going to talk about clustering as well. So that could be one way of doing it. Take all your web pages and cluster it, and those clusters are going to tell what each of these topics are. Keep in mind that this doesn't have to be given an explicit name. It could just be special topic 1, which could be some odd mixture of sports and entertainment, right? Or maybe something else. You don't need to physically know what it is. Once we have done that, the second part is to figure out which topics are of most interest to a particular user or a given query. And this happens from basically, let's say, your search history and trying to figure out how that corresponds to the traditional results for those search results, how they classify onto these particular specialized topics. So the kind of pages that you've clicked. So if you're going through, it gives you 10 results, and you click on the 4th link, means that that is of greater interest to you, and then I can see which of those specialized page ranks gives you that sort of rating. So over a period of time, and again, there are many different ways of doing this. We'll look at some techniques later in the class, and they're related to the first part of the thing of figuring out which ones are important. We can actually build up a profile for a given user, and then the page rank vectors weighted by your own interests are going to be used for ordering the results. Is this clear?
So like once we order the results, right? So without taking the user feedback, is there a way to evaluate how well we are ordering the results?
What do you mean?
Like once you order the results, but you want to know like how efficiently you are ordering, how relevant you are.
For the standard page rank or for
Just page rank.
the standard or the topic specific one? Or the, so simple answer is no, because these are all going to be user specific. There is no best way of defining it. Maybe the best way of defining it is based on how page rank was defined in the default sense, right? So it's going to be specific to you, or it's going to be specific. There's way too much context here. So that is a super hard problem. That's why it's easier to define in terms of the fact that I'm going to tailor it for a specific user or a specific set of users, right? It's hard to define that given these search queries, this is the #1 website. In some cases, it might be easy, right? But not in all cases. If you look at this case, these web pages are going to contribute a certain amount of page rank to this particular web page. And what we are interested, sorry? Yeah, so what we are interested in knowing is that by setting it up, so if this was just a random web page, let's say this is my web page linked by everybody else, I'm going to get a certain amount of page rank. By setting up this sort of a messy structure, how much can we actually end up boosting? So we want to compute Y, right, the page rank of T. What does it actually happen? So each of those supporting pages, right, the fake pages that I create are going to be beta Y by M, right, plus 1 minus beta by N. This is the probability that a random surfer shows up on these pages, which is 1 over N, plus the fact that somebody follows a link from the target to one of the supporting pages, which is going to be beta Y by N. Is this clear? Now, let's compute the page rank of the target. If you consider the target, the probability that somebody shows up here is coming from the probability that he comes up from one of the accessible pages, which we have assumed is X, right? plus a probability beta times n, because that's how many pages we've created, that it shows up from one of our supporting pages. Okay? Plus, of course, the probability that somebody randomly appears on the target itself. Is this clear? Yes? 3 terms comes from the accessible pages, comes from one of the supporting pages, appears randomly.
So once I go into my, once the crawler comes to my page and I keep mirroring back and forth into my farm, is there a way I can go?
No. So that's how we are modeling it.
Modeling, okay.
Fundamentally, this structure is going to be reflected in the matrix. It's not like the crawler is. Don't try to think of the fact that the crawler is physically going back and forth. This is a calculation that we're doing based on the structure of the matrix. And what you have done is to modify the structure of the matrix to basically boost it. How effective do you think this method is?
Depends on my farm size.
Give an idea. How much do you think you can boost? Anyway, let's take a look. So let's simplify that. We can simplify that. So you get y is equal to x plus beta square y plus beta 1 minus beta m by n. I ignored some very small terms. And you can eventually come up with an expression which is like this, that y is going to be x divided by 1 minus beta square. So this, by the use of a spam farm, you were able to boost your score that you would have gotten otherwise by a factor of 1 minus beta square. And in addition, depending on how large m is with regards to the overall internet, that's an additional term that I've been able to give. So there are 2 factors. One, you're boosting your scores, and you're also adding another finite value, right? This is completely in your control. So you can do it. And this is basically, if my input is decent, I'm basically boosting my score. Let's assume that beta is 0.85, which is reasonable, right? That there's an 85% probability that you follow one of the links. And this is probably more realistic to what most search engines would use, typically somewhere between 0.8 and 0.9. How much do you think it gets boosted? The external score for a factor of 0.85 gets boosted by 3.6 times, which is huge. Keep in mind that our probabilities are anyway in the 0 to 1 range, right? And you also have a 0.46 times the percentage. You've also boosted it by that factor. So you really gain a lot from doing these kind of tricks, right? So this is why you will see people going in and putting all of these. This is also the reason that many of these websites now start discouraging. Basically, they don't allow you to put links because they know what it's not that they don't want you to click on those. It's just that these pages are trying to boost their scores. Beyond just the fact that you will follow those links, it affects everybody else as well. So there are 2 standard ways. There are way many more ways. This is just a sort of an idea for you to understand how you would go about making these changes. The first is something called as trust rank, which is basically a variation of topic-sensitive page rank. So now you say that just as we were picking out subsets of pages which were focused on a specific topic, we're saying that these are trustworthy sites, which means that these are very reliable and they are less likely to have links to spam web pages. So now what you can do is that is going to tell me how close it is. More specifically, we can use that to compute something known as a spam mask by looking at how different is the page rank based on these trusted pages, the trust rank, versus if I do not use any tags. And those can then be used to figure out what these, whether these particular page is trying to spam you and increase this page rank. So you can either completely discard that from your transition matrix, or you can just say that I'm going to heavily scale down the page rank for that particular website. Okay. In general, you want to manually select these trustworthy pages. That is one option. You can avoid trustworthy sites, and you also should avoid trustworthy sites, let's say New York Times, which allows you to go and input comments, right? those no longer are trustworthy, even though the content themselves might be, but the fact that they can be set up as an accessible website makes it less attractive to use for these kind of things. You can also use sort of specific domains, like .edu, .gov websites where unauthenticated people or the membership itself is limited. Keep in mind that we want only something in a probabilistic sense. So although somebody like you might have your own .edu website and adding spam links out there, probabilistically most of those links coming out of these kind of controlled websites are probably going to be non-spam. So those are good ways to do it as well. You can look at clustering the next time.